So I will introduce our next speaker. Today we have Chris Bartel. Chris is a postdoctoral scholar at UC Berkeley and Lawrence Berkeley National Lab, working in the group of Professor Jurban Cedar, where he uses computational materials science and statistical learning to understand the nature of solid-state material synthesis. He uses this modeling work to accelerate the advancement of energy conversion and storage technologies using new inorganic materials. Prior to this, he attended Auburn University to earn a BS in chemical engineering before earning a PhD at the University of Colorado Boulder with support of an NSF graduate research fellowship. Under the guidance of Professors Charles Musgrave and Al Weimer, he was named the CU 2018 Max Peters Outstanding Graduate in Chemical Engineering after his accomplishments in research and authoring 11 papers in major journals and giving numerous presentations at AICHE, national meetings, and other conferences. So thank you to Chris, and give him welcome for his speech today.
All right, thanks a lot, Sawyer, for the introduction. Is this too loud? What do you think? Sounds good? All right, cool. And yeah, thank all of y'all for attending my seminar and giving me a tour of the department and providing me with some helpful advice and feedback on how best to navigate the future of my young academic career. So today I'll be giving an overview of my PhD thesis work, which we use density functional theory and machine learning techniques to try to develop these predictive descriptors for the stability of new solid-state materials. So just to briefly give an agenda of where I'll go in this talk, so I'll give an overview of how we think about solid-state materials design and discovery, and then focus on each of three different projects. So first, explaining what I mean by descriptors, and then how we apply this to predict the stability of perovskites. Thinking about how we extend DFT predictions, which are nominally at 0 Kelvin, to include temperature effects, which are more relevant to especially the synthesis of solid-state materials. And then finally, just a story of how we've successfully gone through the whole materials discovery pipeline, from proposing theoretical compounds to eventually synthesizing new materials in the lab. So if we take a brief tour through the history of solid-state materials, we see that throughout history, these have made a landmark step forward in how we think about technology and progress within society. So a short 5,000 years ago, early people discovered that if you added a small amount of tin into copper, you could increase the ductility or hardness depending on the ratio of copper to tin. So this perhaps represents the first solid-state materials discovery or design, where we found that we can change the material or the properties of a solid-state material by tuning the composition in chemistry. So if you fast forward a couple thousand years, we can think about central processing units and how silicon has transformed the way we do computations and really carry out everyday life. And then more recently, thinking about new lithium-ion cathodes or gallium nitride, which is used prevalently in the solid-state lighting industry. So as we look towards a fossil fuel-free energy sector moving forward, we're going to have to continue to develop a variety of solid-state materials that might form the basis of catalysts, next-generation batteries, photovoltaics, superconductors, and so forth. So fundamental to the implementation of any solid-state material in endgame application is that we can answer this question. So given some arbitrary arrangement of ions in a periodic solid, is the material stable? So if the material is unstable, then we should really move on to the next material, because it's unlikely that this material will ever be implemented in one of these devices where we expect a long-lived lifetime. So we need this solid-state material to survive on the roof of a house or in the battery of a car for 10 to 20 to 30 years. And so if it's thermodynamically unstable, this is unlikely to happen. But if it's thermodynamically stable, then we can start to think about how that material might be engineered to have optimal properties for one of these applications. So the way we think about thermodynamic stability within density functional theory is using the convex hull phase diagram shown here. So using density functional theory, which is a quantum chemistry approach, given a periodic solid or a solid-state crystal structure like the one shown here, we can obtain what is the energy as a function of the positions of electrons within that structure. So we can obtain 1, what is the optimal structure given the chemistry, and then 2, what is the energy of that optimal arrangement of ions and electrons. From the total energy, we can relate that to a thermodynamic quantity, here the formation enthalpy of that compound. And then what we do is, if we specify a specific chemical space, in this case, this is the fraction of sulfur in manganese sulfides. If we take all known materials that sit in this chemical space, we can plot their formation enthalpy as a function of composition, and then we join any of these points by the largest possible convex object. So that's not terribly important, but this is called the convex hull, and so that's shown by the blue line. If a point lies on this convex hull in this energy composition space, then it's thermodynamically stable, and so it's likely that we'll be able to make this structure if we perform synthesis. Conversely, if it's above the hull, shown by this red triangle, then it has some thermodynamic driving force for instability or decomposition into these thermodynamically stable phases. And so this is generally how we think about material stability in the context of density functional theory. However, while this technique does a really good job of telling us whether one material is stable with respect to another, if we open up the design space, and we're forced to make a few specifications before we're able to obtain this convex hull phase diagram picture. So first we have to specify the chemistry. In this case, we're looking at manganese sulfides. We have to specify the composition of each potential stable material. So here is 1-to-1 ratio of manganese to sulfur, 2-to-3, and so forth. And then finally, we have to determine the structure. So what is the structural ground state given this composition in chemistry? So in unconstrained composition and structure space, where we want to look to search for new materials that might be the next generation battery or solar cell, there's really a lot of specifications that a human has to make as far as what are the inputs before we can determine their stability with DFT. So just to illustrate what kind of combinatorial design space exists in solid state materials discovery, there are about 60 relevant elements to a solid state material. So these are all that are present in the Earth's crust. We can combine them in a number of elements with one another to make a diverse range of solid state compounds. Then if we think about composition, if we look to a few recent Nature papers that studied lithium-ion batteries, LEDs, or proton conductors for fuel cells, so the materials that are really at the forefront of solid-state materials design often have multiple elements. So in this case, we need lithium, manganese, niobium, oxygen, and fluorine before we're able to make this cutting-edge state-of-the-art cathode. And so that increases the combinatorial design space. So then finally, we know that the structure of solid-state materials controls much of the properties. So here, for instance, I'm showing for this lead halide perovskite phase, the cubic alpha phase has this photoluminescence peak, but if a slight structural transformation occurs to this delta phase, which is, again, the same chemistry and composition as this formamidinium lead iodide, we get no photoluminescence. So just by a slight tweaking of the way the ions are arranged in the lattice, we can go from a material that looks good for a solar absorption to a material that has no solar absorption. And so in practice, there are on the order of hundreds to thousands of possible structures that can be occupied for a given chemical composition. So what this leads to is that if, let's say we specify some ordering or composition of some imaginary elements, A, B, C, D, then we have, say, 100 possible structures, 60 elements that can be each of A, B, C, or D, and ultimately about 100 million possible materials that we would have to evaluate even after we fix these ratios to be 1 to 2 to 3 to 4. So it's clearly not possible that we'll have to use a computationally expensive technique like DFT to be able to calculate the stability of all 100 million of these materials. And so what that's motivated in the space of computational material science is this theme of research termed materials informatics, which really follows the lead of bioinformatics and cheminformatics, and tries to incorporate this fourth paradigm of science, so statistical or data-driven approaches, to try to accelerate how we can find these next-generation solid-state materials. So this will really be the driving question behind most of my PhD work, is how can we integrate these paradigms and especially use density functional theory and statistically driven approaches to understand the stability of new solid-state compounds. So the first story I'll talk about is trying to find a descriptor for the stability of this perovskite structure. If we take a step back and think about crystal structure prediction, this is a pretty classic problem in solid-state chemistry. Basically, we have some chemical formula, in this case AB2, where A and B are elements, and we want to know what is the crystal structure that this chemical formula is likely to manifest. So once we know this crystal structure, then we can start to think about what properties will that material have and what applications are going to be good for that compound. So we can do this with density functional theory, usually using some kind of optimization technique like a genetic algorithm, but it's extremely expensive. So here in one case, I'm looking at magnesium silicon oxide, and in this classic paper on a genetic algorithm crystal structure prediction, It required 3,200 DFT calculations before they ultimately found what is the ground state structure for this composition. So again, if we have a really large design space, using a technique that's this computationally expensive is not going to be tractable. So even before the development of DFT, early chemists had been thinking about this idea of crystal structure prediction, most notably Linus Pauling. So Pauling came up with several rules that help you identify what is a likely crystal structure given the chemical nature of the elements involved. And one classic example of a descriptor or structure map is shown here, where if we take some simple binary cation-anion material, so this might be magnesium oxide or calcium sulfide, so forth. If you plot the radius of the cation against the radius of the anion, then you can actually obtain a pretty good guess of what will be the coordination of the anion around the cation in a ground state crystal structure. So if we have a large anion and a small cation, then we're likely to have a low coordination number, meaning we can only fit a few anions around that cation. So in the opposite case, if we have a large cation, small anion, then we can start to pack a large number of anions around that large cation. So these kind of empirical descriptors for structure have been developed often 100 years ago, 80 years ago, but they're still being used today to drive at least making an initial prediction of what is likely to be the ground state structure for a given material. So in the age of statistical learning and data-driven approaches, we wondered if we could use machine learning to advance these theories to develop more predictive descriptors that don't just give a qualitative indication of structure, but actually predict the stability of new materials. So taking a step back and thinking about what makes a good descriptor, especially in terms of the physical sciences, I'll walk through a few tenets that I've tried to follow, at least in my PhD work. So if we're thinking about what do we want to use machine learning to predict, an initial criteria is that developing this model or a shortcut to the prediction is useful for some community. So a classic example of this in chemical engineering are these volcano plots that using just a handful of DFT calculations of adsorption energies of some gaseous species, we can determine with reasonable accuracy what is going to be the catalytic activity to perform some reaction that includes this intermediate. So in this case, we can see that platinum lies near the top of the volcano. So before doing any kinds of experiments, we can predict what is going to be the catalyst activity as a function of this binding energy of oxygen. So as a contrast to what would be a useful descriptor, this would certainly not be useful. So just predicting whether my dog is going to catch this ball that I throw to her. So while she and I might be interested in whether she's going to catch this so that I have to wonder if I have to track it down after she misses it, most of the material science and chemical engineering community is probably not going to care. So it's not really worth developing a machine learning model based on her coordinates to predict whether she'll catch this tennis ball. So the second criteria is that, so we know it's useful for some community, we need this model to make reliable predictions. So if I imagine the distribution of some target property that we're trying to predict, this might be the total energy or band gap or some figure of merit for the material, plotted against some candidate descriptor. So if we have a model that looks like this, I know there's a big data science emphasis at UW, so I'm sure you're familiar with this classic overfitting example. Basically, we're able to predict what are the training data points? So this model does quite well. But if we were to give this new data or make new predictions, then we can't really expect this to be generalizable outside of the training data. So this would be a classically overfit model. In the opposite case, we could have an extremely simple model that we understand the actuating mechanisms of how this descriptor makes predictions of the target. But if it's not accurate, then people are not going to use it to actually successfully make new materials or predict some property. So ultimately what we want is a simple descriptor or a simple model that does in fact make accurate and generalizable predictions. So as the final step, as a physical scientist developing machine learning models, I think it's important to always have these applications in mind and be able to generate or demonstrate some utility of the descriptor that you find. So oftentimes in the computer science community, they might develop some new machine learning algorithm and show that it performs very efficiently and it can predict training set and target and test set points. But what's often lacking is this connection between how someone might use the model and actually design a new material or some application that's relevant to the physical sciences. So with this in mind, my collaborators at the Fritz Haber Institute developed this algorithm called Ciso, where the basic idea is how can we come up with these physically interpretable descriptors given some fundamental properties of a system? So for instance, one example might be I start with a handful of primary features like the mass, ionization energy, electronegativity of a compound. And then I systematically construct these symbolic models. So I might have ionization energy divided by electronegativity, electron affinity plus ionization energy, and so forth. So ultimately, I perform this iterative scheme of making more and more complicated, physically meaningful expressions until I have about 1 billion candidates. So once I have a large set of candidate descriptors, the first step is to perform CIS, or Shor independent screening, which just provides a quick metric of how well does this candidate feature correlate with the target property. So essentially what I do is I rank every candidate descriptor in this space from 1 to 1 billion using a very computationally efficient metric. So now that I have a ranking, I select some specified subset of that ranking. So let's say the top 1,000 of these candidate descriptors. And then I apply a more sophisticated machine learning algorithm like a decision tree or a support vector machine to say what is the single best descriptor from this reduced space. And then if I'm not happy with a very simple model, I can kind of perform this scheme iteratively, constructing more and more higher dimensional but potentially less meaningful descriptors until I have a desired degree of accuracy. So now connecting back to the space of interest for this work is predicting the stability of the Perovskite structure. So perovskites are defined by this ABX3 formula where A and B are cations and X is an anion, typically oxygen or a halogen. And the characteristic nature of the perovskite structure is that you have a large A site cation that's surrounded by this corner-sharing network of BX6 octahedra. And what's useful about perovskites is that they have a number of interesting properties, especially in optoelectronics. So very recently there was a special issue in Science just kind of highlighting the value of perovskites for various things like light emission or light absorption. And so these are fundamentally interesting materials from a design, from an application design space. So because perovskites have been discovered a long time ago in the 1800s, one of the early solid-state chemists, Victor Goldschmidt, developed this empirical tolerance factor much in the spirit of what Pauling did years later to try to say, at least qualitatively, what is the likelihood of forming the perovskite structure given this chemical formula ABX3. And so the way this parameter T works is it just relates the ionic radii of each ion in the chemical formula and states that based on geometrical constraints, if T is equal to 1, then the material has some degree of likelihood of forming in this perovskite structure. As it deviates from 1, this becomes less likely. So if we look now just a couple years ago, this parameter is still being used prominently as a at least qualitative indicator of whether the perovskite structure is going to be stable. So in practice, what people do, because this is just an empirical parameter, is they extend this criteria from instead of T equals 1, we say we expect perovskite if T is in the vicinity of about 0.8 to 1. So as an initial step, I assembled a small database of all the ABX3 compounds that have been experimentally characterized as perovskite or non-perovskite at ambient conditions, and then first said, what are the optimal bounds on Goldschmidt's tolerance factor that best separates non-perovskites from perovskites? And what we find is that Goldschmidt's parameter actually does pretty well. It's able to classify about 3 and 4 of these materials as whether they're perovskite or non-perovskite. So this is pretty valuable because the only input is the chemical formula. So we can just write the chemical formula, evaluate Goldschmidt's parameter, and then have a 3 and 4 likelihood of getting it correct whether that material will actually manifest as perovskite. However, a principal fallback of Goldschmidt's parameter is this large degree of non-perovskites which sit in the perovskite class that's predicted, this region of about 0.8 to 1. And so we call these false positives. And it turns out the false positive rate with Goldschmidt's parameter is about 50%. So it's actually quite high. So then, using the same input parameters, the ionic radii and the oxidation state of the A-site cation, which is itself an input to these ionic radii, we use Ciso to develop this new tolerance factor, tau. And what we find is that tau significantly improves upon Goldschmidt's parameter in terms of predictive accuracy, and it's able to separate perovskites from non-perovskites using a single decision boundary. So because it just separates perovskites with this one line, we call it a monotonic classifier, which basically means all the perovskites are on one side of the line and the non-perovskites on the other side of the line. And this is a bit different than Goldschmidt's parameter, which tries to sandwich the perovskite class between these two non-perovskite places. So this might seem a bit semantic, but it actually has significant consequences for what you can do in terms of extracting probabilities of forming perovskite using each of the descriptors. So using a technique called Plat Scaling, we can obtain, as a continuous function of tau, what is the probability of forming perovskite? And that allows us to construct these structure maps. So here I'm showing the radius of the A site cation versus the B site cation for larger and larger halogens on the X site. So these dark red regions mean these are radii combinations that are very unlikely to form perovskite, and then this small blue region means we're likely to form perovskite in this space. So because we use Ciso to develop a model, we have this kind of tangible descriptor that we can play around with and try to understand how the learning algorithm or how the model is actually making predictions. So this might be in contrast to something like a neural network where it's more opaque how the inputs are turned into the outputs. So one thing we can do is start looking term by term at this descriptor and think about what are the consequences or why did the learning algorithm pick that term. So if we look at this first one, this is just the radius of the anion over the radius of the cation, which is exactly the empirical descriptor that Pauling developed in that first structure map I showed. So all this parameter is indicating is what is the likelihood of coordinating the B site cation with 6 anions as is needed for the perovskite structure. And so this manifests also in these probability maps where as we move to larger halogens to the right, we need larger and larger B site cations to be able to form these stable octahedral units. Similarly, we can look at this more complex term. So this is the cation radii ratio divided by the log of itself. And at first this might look a bit suspicious or strange that the learning algorithm would pick this kind of term. But the way it manifests in the probability map is that when these two radii ratios are equal to one another, or when the ratio equals 1 or the two cations have similar size, then the probability of forming perovskite goes to 0. And so that's evident by this dark red region right around the y equals x line. And now thinking about the perovskite structure and why that particular signature might be present in the model, we know that the A site cation must be 12-fold coordinated by the anion, whereas the B site cation forms these octahedra or 6-fold coordinations. So if the radius of the A site and the radius of the B site are very similar, it's highly unlikely that the ground state configuration of this formula will include such a diverse coordination environment for the two cations. And so instead of the perovskite structure that has A coordinated by 12 and B coordinated by 6, we might find alternative structures where the coordination number is similar between these two cations. All right, so the final piece of what makes a good descriptor is demonstrating some utility. So one place we looked to extend the model was to these double perovskites. So a double perovskite is just this ABX3 formula, but we consider 2 possible B sites. And so now we have this, in the ideal case, an alternating network of BX6 octahedra around the large A site. And so what this allows us to do is, in one example, take a cesium lead chloride, which is a good direct gap semiconductor, and we can replace lead with silver and indium. So remove the toxicity of lead, but still have this direct band gap. So if we apply tau to these materials by simply taking the average radius of the B and B prime sites into an effective B site radius, with no further training, we can get about 9 in 10 of these materials classified correctly. So that suggests tau is generalizable outside of the data it sees during training. Now we want to actually use tau to find new materials, and so we target this chemical space, cesium chloride double perovskites, and we write the chemical formula for all possible double perovskites in this space, which is about 1,000 different materials. Tau tells us that about 300 of these sit in this region that are expected to be perovskite, and so we try to confirm or reject their stability using DFT. So once we calculate their stability or the decomposition enthalpy using the convex hull formalism I showed earlier of all 300 of these materials, we ultimately find that most of these are in fact stable with a few exceptions. And then importantly for the design of new optoelectronic materials, we find a number that have band gaps that are relevant either for light absorption or light emission across the visible spectrum. And so just summarizing this talk, or this portion of my talk, so we use Ciso to develop a new tolerance factor tau that improves significantly on the gold standard, or the previous gold standard. We show that because tau is a simple expression, we can obtain these probability maps and also extract what is the meaningful consequence of each of these parameters in the descriptor we find. And then finally, we demonstrate a mechanism by which we can use tau-based predictions to try to identify new materials for optoelectronic applications. So now transitioning to another project where we use Ciso, this time trying to come up with a descriptor for temperature effects of solid-state materials. So one thing I didn't point out earlier when I showed this convex hull phase diagram is that the energy quantity that we typically use in high throughput DFT calculations is the formation enthalpy at 0 Kelvin. So it's very, it's computationally tractable to obtain a temperature independent quantity for energy using DFT. And so typically as an initial screening, we ignore the effects of temperature. However, we know that temperature is in fact an important role, especially in the synthesis of solid-state materials, where often we have to heat up materials in excess of 1,000 Celsius before we get any ions to move or before we're able to actually synthesize a target compound. So what I'm showing here now is a temperature-dependent convex hull phase diagram, where now the energy quantity of merit is the Gibbs energy as a function of temperature, which includes the entropic effect of the solid state and of all competing phases. So one example here in the manganese oxide system is that this compound MnO2, if we look at the convex hull in the absence of temperature, we see it's a stable phase. But if we look at temperatures that might be relevant to solid state synthesis, eventually it moves above the convex hull and becomes thermodynamically metastable. So we are able to do this with density functional theory, that is, capture the temperature dependence and obtain this Gibbs formation energy as a function of temperature. However, it typically requires on the order of 100 to 1,000 times doing a single 0 Kelvin calculation. And so it's not really tractable to do this in a high throughput search where we're considering many possible materials. So that motivates us to develop a new model to predict this solid state temperature dependence. And so if we think about eventually the property we need is this Gibbs formation energy as a function of temperature. So for a material, that means we need the absolute Gibbs energy of that material minus the elemental free energies that make up that compound. So here, in the case of manganese oxide, we need the vibrational free energy of manganese oxide subtracting away the free energy of manganese and the free energy of oxygen, which gives us this delta G of formation from the elements. So these elemental free energies are really easy to obtain because they're all tabulated from experimental data because there are only a limited number of elements in the periodic table. So next, we know that using high throughput DFT, we can get a really good estimation of this formation enthalpy at 0 or ambient conditions. And so I call this relatively easy DFT. So there's existing high throughput infrastructure to determine this quantity for many thousands of materials. So what that leaves is we need to determine this quantity G delta, which is the difference between the absolute Gibbs energy of the compound and the formation enthalpy in the absence of temperature. So what I'm showing here are for 300 compounds with experimentally extracted quantities for this G delta, where each of these blue lines represents a different material. So the first thing we notice is that all of these are actually relatively similar. So they all kind of have this curvature and they all exist within a similar domain of expected values. So these 300 materials roughly span the periodic table and encompass a wide range of inorganic solids. So what the machine learned descriptor was really going to have to do is determine which of these materials have steep GFT curves and which are shallow. And so that's what we did using Ciso again. So we input some relatively fundamental quantities of these materials, and we come up with this slightly more sophisticated expression. So in this expression, we're predicting what is the Gibbs energy of the solid phase as a function of the atomic density, the reduced mass, and temperature. And so for a training set and a test set, we find relatively good agreement between the experimental values and what's predicted using our descriptor. Ultimately, the mean absolute error on the test set is about 45 MeV per atom. And so to give a general idea of how accurate that is, we also look to these explicit DFT-based calculations of the phonon free energy using the quasi-harmonic approximation. So this is using that computationally expensive technique I mentioned earlier. And what we find is that their error bar is about 40 MeV per atom. So somewhat remarkably, using just this simple model that includes 3 fit coefficients, we're able to get close to this really computationally expensive approach. So again, we have this relatively tangible descriptor, so we can start to parse out what is the meaning of the relative terms. So the incorporation of temperature is not so hard to explain. We know that intrinsically the Gibbs energy is the enthalpy minus the temperature times the entropy. So we inherently already have this negative temperature dependence. We can also look at these slightly more involved terms. So this is the atomic density, so how packed are the atoms together, and this is the reduced mass. So if we think to a simple harmonic oscillator where we have a mass attached to this spring of stiffness K, we know that the angular frequencies of these vibrations is proportional to that stiffness over the mass. So it turns out that in solid state materials, the primary driving force for the Gibbs energy is the vibrational free energy. And so ultimately, we can take what are the phonon frequencies of these vibrations, we relate that to the entropy and ultimately to the Gibbs energy. So the way these terms manifest themselves in the solid state is that we have some masses attached to each other by chemical bonds, and these chemical bonds have some stiffness. And so we presume that the atomic density in our descriptor is just acting as a surrogate for what is the stiffness of those bonds, under the thinking that a material that's more dense has stiffer bonds, which is not too much of a reach. And so then the masses are included directly. And so now we have a surrogate for what are these phonon frequencies in our descriptor, which gives us an idea or allows the descriptor to make predictions of what is that vibrational entropy and ultimately the vibrational free energy. So now trying to demonstrate utility of this descriptor, one obvious application is in high throughput predictions of reaction energetics. So here I'm showing the Gibbs energy of reaction against temperature for a sampling of solid state reactions, comparing experimental values, so using Gibbs energies from experiment, and then our model as shown as the dashed lines. And so we have these relatively diverse set of reactions, and we find that the descriptor actually does pretty well in capturing these reaction-free energies. Now we can move to a slightly more sophisticated test case. So here I'm showing an expression for Gibbs energy minimization. And so the basic idea here is that we can feed or we can propose an initial feed to an imaginary reactor, in this case molybdenum nitride and water, and then we use this technique, Gibbs energy minimization, which says these materials at equilibrium will change state to minimize their collective free energy. So that could mean the oxidation of molybdenum nitride to molybdenum oxide. It could mean molybdenum oxide reduces to solid molybdenum. So basically this optimization program says these materials will find their minimal free energy state subject to the constraint that this is a closed system with respect to transport of solid state species or the transport of any atomic species. So if we start the reactor with 2 moles of molybdenum, we need to find the distribution of products that still has 2 moles of molybdenum in it. So if we perform this Gibbs energy technique using experimental free energies or the ones we generate using our descriptor, now for this relatively complex system, we still get pretty good agreement between what is the predicted speciation of each of these components as a function of temperature. So one place that we can look to leverage this technique of high throughput Gibbs energy minimization is for chemical looping processes. So one of those is shown here. So this is a recent cycle proposed in 2007 to generate ammonia using a redox chemical looping type setup. So we start with a metal nitride. We expose it to steam at moderate temperature. This oxidizes the nitride to the metal oxide and generates our valuable product ammonia. So now we have a metal oxide that is then reduced in the presence of some reducing agent, such as hydrogen, and now at very high temperature, to form this metallic state, so basically decomposing the oxide to the metal. And now in the final step, this metal is used to reduce atmospheric nitrogen, form the metal nitride, and allow us to reproduce this cycle. So eventually nothing is consumed except air and water, and in theory we can generate ammonia just by cycling between the oxide and nitride. So ultimately this is a very challenging process thermodynamically because it's very difficult to find an oxide that is able to be reduced by hydrogen at even moderate conditions and still find a metal that interacts with nitrogen favorably enough to form a metal nitride. So what we wanted to do is try to search for what is the optimal cation to mediate this interconversion between nitride and oxide. And so we start with the Materials Project, which is an open database of DFT calculations at 0 Kelvin. This generates about 1,100 candidate redox pairs, so candidate materials that might cycle between nitride and oxide. So then what we do is use our descriptor to account for the temperature-dependent component, and we screen all of these materials for what is their yield per cycle of actually generating ammonia and being able to cycle back between nitride and oxide. So it turns out this is a really bleak story. So we looked at about 1,100 materials, and none of them are viable at equilibrium. So if we perform this Gibbs energy analysis for each of these reaction conditions, we find no materials at equilibrium that are able to interconvert between nitride and oxide even considering temperatures as high as 1800 Kelvin. So this is a bit of a dark story for the purposes of solar thermochemical ammonia synthesis, but there is perhaps some light at the tunnel if we consider Le Chatelier's principle. So in a lot of these chemical looping type processes, we can control what is the relative partial pressure of our gas phase species. So in this case, I'm showing the reduction of iron oxide in the presence of hydrogen, where this term X is that ratio of reductant to oxidant. So here, if we have a 1-to-1 ratio, which is the natural equilibrium for this cycle, we get almost no yield, even up to very high temperatures. But if we start to consider the imaginary scenario where we can remove steam at a high rate or flow excess hydrogen in the reactor, then we can start to see some substantial yields. And so it's possible that if you were able to operate this reactor under these conditions of high reductant to oxidant ratios, that these relatively earth-abundant and cheap materials based on iron and vanadium look okay for this process and might deserve further investigation. So to recap this portion of my talk, so we again use Ciso, this time to develop a descriptor for the Gibbs energy of solid-state materials. We showed how this can be used in conjunction with Gibbs energy minimization to generate these high-throughput speciation diagrams. And then finally showed how this might be applied to screen materials for a chemical looping process, in this case ammonia synthesis. So for the final portion of my talk, I'll describe a collaborative effort between the University of Colorado, NREL, and Lawrence Berkeley National Lab, where we went start to finish through the materials discovery pipeline to try to identify new metal nitride semiconductors. So here I'm showing what is the prevalence of oxide semiconductors as a function of year compared with nitride semiconductors. And so what we find is that there are about 40,000 reported ICSD, which is the Inorganic Crystal Structure Database. So basically all known solid-state materials, for the most part, sit in this database. And what we find is that there are about 40,000 known materials that contain oxygen compared to about 3,000 that contain nitrogen, with a lot of those just discovered since the Nobel Prize was awarded for the blue LED. If we think about why this is the case, so both oxygen and nitrogen are extremely abundant in Earth's atmosphere, but you find no naturally occurring nitrides in the Earth's crust compared to thousands of naturally occurring oxide minerals. And so fundamentally, this comes down to the fact that the bond energy of diatomic nitrogen is about half that of diatomic oxygen is about half that of diatomic nitrogen because of the triply bound nitrogen compared to the doubly bound oxygen. And so what this means is that if oxygen and nitrogen are present, a metal is always going to dissociate oxygen instead of nitrogen. And so you'll form these oxide minerals in the Earth's crust instead of nitrides. However, there's some advantages to looking into nitrides, especially for semiconducting or optoelectronic properties. So here for the case of gallium, we can see that gallium oxide is an insulator. It has a very wide band gap. But if we combine that with nitrogen, there's different chemistry going on in the solid state, which changes the electronic structure and ultimately leads to a smaller band gap semiconductor that has nice charge transport properties for the purposes of LEDs. And so because we know that the relative proportion of oxides to nitrides is extremely high, it's likely that there are a lot of nitride semiconductors sitting there waiting to be discovered that might have exciting properties for some application, much in the spirit of gallium nitride. So in step one of our high throughput scheme to discover new nitride semiconductors, we use a technique called data-mined ionic substitution prediction. And in this scheme, we might know that there's a material, magnesium zirconium nitride, that has this composition, so 1:1:2, and this crystal structure. And so imagine that this is a known material. Then the way this substitution prediction algorithm works is that it generates a probability that substituting one of the ions on any of the site for a chemically related ion will likely lead to a stable structure. So in this case, if you substitute zirconium with an element in its same chemical family, titanium, in the same structure, then you do indeed find that magnesium titanium nitride is also a stable compound. So we kind of repeat this analysis for all possible permutations of all known materials and generate about 6,000 materials that have some plausible likelihood of being synthesized as a metal nitride. As the next step, we construct these convex hulls using DFT calculations for all 6,000 of these materials and all of their possible competing phases, so that within each ternary nitride chemical space, we can generate this convex hull and assess whether any or some of these predicted materials are actually stable within the construct of DFT. So ultimately what that leads to is this stability map, where what I'm showing is cation 1 in the ternary compound against cation 2, where each of these blue spaces indicate a stable ternary nitride exists in that chemical space. So what we find is that while we started with a large number of materials, about 6,000, only 244 of them are predicted to be stable with DFT. This is actually quite remarkable because there are only about 213 known metal nitrides that are already stable. So we reproduced the stability of these compounds to try to confirm the realistic nature of these predictions. And so ultimately what we're doing from a theoretical standpoint is doubling the space of ternary nitrides that are known to be thermodynamically stable. So we also made an interactive version of this map. So an experimentalist looking to discover new materials can just hover over one of these squares, in this case molybdenum and zinc, and then immediately get the calculated thermodynamic phase diagram for the zinc molybdenum nitride chemical space, and then also get information about which of these compositions are newly predicted or already exist in the ICSD and so forth. And so at NREL, they have expertise in combinatorial sputtering of nitride materials, and so they use this interactive map to try to target what are some metal nitrides that they're interested in synthesizing from an optoelectronic perspective that we also predict to be stable. So ultimately what they find are 7 new nitride materials, which historically, since the 1920s, the average rate of discovery of metal nitrides has been about 3 per year. And just in the course of this one study, they were able to find 7 new materials that are stable as thin films in this ternary nitride space. It's pretty remarkable. So because I'm not an experimentalist, I won't go into too much detail about these materials, but some of them have unique optoelectronic properties that haven't yet been reported in the metal nitride space. So what this shows is through these 3 steps, we're able to go from a starting point of just wanting to discover new metal nitride materials, using some data mined predictions, high throughput density functional theory calculations, and ultimately experimental confirmation that these materials, or at least some of these materials, exist in the real world. So this is pretty good, and it's really a nice confirmation as someone who just does theory to actually see these materials be synthesized. But because we did all these DFT calculations, we kind of have a lot of data sitting there that's not necessarily being utilized. And so we tried to think about what else we could possibly learn from this data. So we wanted to understand from a first principles perspective what is driving stability in the ternary metal nitride space. And so we started from this very classical picture by Van Arkel of a chemical bonding triangle. So in this type of analysis, what you do is plot the electronegativity difference between the ions in a compound against the average electronegativity. And so what you'll find for some simple binary compounds is that these intermetallics or alloys sit near this metallic corner, very ionic compounds sit at the top of the triangle, and then very covalent compounds sit at the bottom right of the triangle. And so this is an approach that's typically taught in general chemistry or in early chemistry classes. And it's incredibly instructive just to think about how the electronegativity of ions affects the chemical bonding makeup of these materials. However, we have density functional theory calculations for a large number of materials. So this is a lot of information that we have sitting there in the charge densities and the calculated electronic structures. So we wanted to think about, instead of electronegativity, reinventing these axes using these first principles based calculations. So as a first step in doing that, we tried to think fundamentally about what is the difference between each of these axes from a fundamental standpoint. So we think about metallic bonds versus covalent bonds. These are both just a type of charge sharing. So they're both covalent bonds, but metallic bonds are delocalized and covalent bonds are perfectly shared between ions. And then similarly, if we go from this bottom axis to this top axis, this is really just changing the degree to which charge is transferring between ions. So in the covalent case, we have perfect charge sharing. In the ionic case, perfect charge transfer. And so trying to stay out of the weeds for the most part, we developed these ways to partition the DFT calculated charge density first into a metric to quantify what is the covalency of a periodic solid. And so we do that using this COP approach, or crystal orbital Hamilton populations, basically determining what is the degree to which electrons are overlapping in all the orbitals in the solid state material, and then weighting that as a function of energy to say that if orbitals are participating in covalent bonds at very negative energies, then those are very covalent bonds. So we ultimately capture that as this energy-weighted integral of these COP populations, or sigma. And so what I'm showing here is two polymorphs of gallium oxide, the ground state alpha phase and the higher energy beta phase. And so we see that the sigma for the alpha phase is larger than the beta phase, meaning the covalent interactions are stronger in this structure of gallium oxide than in this one. And we can use that to try to understand why this structure is the ground state and this one is the polymorph. So just looking at these crystal orbital overlap populations, we can say that there's more covalent interactions in the alpha phase, so it's plausible that this is the reason why it's the ground state instead of the beta phase. So now this kind of gives us our local or our covalent axis, but then to assess how local are those covalent bonds, we decouple this sigma into covalent interactions that include nitrogen. So these are metal to nitrogen bonds that we expect to be nominally covalent, and bonds that just include cations. So these are just metal-metal interactions. And so we're decoupling what is the sigma just for these interactions and just for these interactions. And so that makes up our metallic and covalent corners of this plot. So now we need to come up with a comparable quantity that characterizes what is the degree of charge transfer or ionicity. And so to do that, we start from some very fundamental properties, the first being the net atomic charge. So if we think about the ideal case of sodium chloride, sodium is happy to give one of its electrons to chlorine, and so we call the net atomic charge 1, because there's one electron transferred from one ion to the other. We use another pretty fundamental quantity, which is the bond order. So in the case of diatomic hydrogen, we have 2 electrons in bonding orbitals and 0 in antibonding orbitals. So the bond order is just 1/2 of 2 minus 0, or 1. So we can then assess what is the ionicity of a given material by this ratio of net atomic charge to bond order, so delta over S. This is basically telling us what is the number of electrons transferred divided by the number of electrons bonded. So if we have no electrons transferred, that's a covalent interaction. Then if we start to have some directionality in those covalent bonds, so we have some electron transfer, but most of them are shared, that's like a polar covalent bond. And then finally, if all of our electrons are transferred, then that's an ionic bond. So that makes up each of the corners of our new first principles derived bonding triangles. And so what we see is if we map the chemical space of the ternary metal nitrides onto this map, we get some interesting features. So first, I'm partitioning this triangle into compounds that include an alkali metal. So these are classic solid-state materials that are typically stabilized by what's called the inductive effect. And so this usually leads to a high prevalence of nitrogen-rich compounds and accounts for the vast majority of our stable data set of ternary nitrides. So the more unusual and perhaps more interesting compounds are these metal-metal nitrides, where both cations are a transition metal. So historically, these have been very sparsely reported. And what we find is that these materials are usually nitrogen poor and sit along this metallic corner of the triangle plot, with the unique exception of zinc-containing compounds, which our experimentalists find that when they try to synthesize zinc metal nitrides and magnesium metal nitrides, they see very similar characteristics. So effectively, these zinc-containing compounds are behaving a lot like these classically inductively stabilized ternary metal nitrides. So I can walk through these diagrams a bit more. So if we just imagine this cartoon of an electropositive A cation, a more electronegative B cation in nitrogen, for these alkali metal nitrides that typically sit along this covalent ionic axis, what we imagine is happening is that this electropositive A site is happy to give up one electron. Nitrogen, being the most electronegative element in the system, is happy to accept this electron. And what that leads to is a rich network of these BN bonds, or a covalent framework of a BN polyhedra. And because this B atom is now so happy to bond with nitrogen, it actually gets oxidized relative to its charge state in the binaries. And so we need more nitrogen to accommodate this excess charge. And so this is really what's described in the classical inductive effect, where you have some electropositive cation just stabilizing some covalent network of a more electronegative cation interacting with an anion. So the way this manifests in the map is with all of these green nitrogen-rich compounds. So it's again nitrogen-rich because of the oxidation of the B site cation that sit along this covalent ionic axis. So in our triangle plot, we're not partitioning the difference between this ionic interaction of A with the BN network or just this covalent interaction. And so what happens is these get averaged into being half ionic and half covalent, which is kind of the picture we get just thinking about the inductive effect. So now looking at these arguably more interesting materials, we propose that these materials are stabilized by the reductive effect. So these are compounds that have transition metals sitting on both cation sites. And these usually have these strange crystal structures that involve some kind of network of metal-metal bonding. So in this case, the two cations have similar electronegativity because they're both transition metals, and then nitrogen is much more electronegative. So what we find that's actually quite interesting is that nitrogen gets oxidized relative to its charge state or the amount of charge density around it in the corresponding binary nitrides. So in order to form these materials, we're actually reducing the two cations and forming this metallic network of cation-cation bonds and liberating nitrogen to accommodate this reduction of the cations. So we get these very metallic and very nitrogen-poor compounds that sit at this metallic corner of our bonding triangle map. So in the course of this paper getting accepted, a few of these materials actually were synthesized separately and found to exhibit unique properties such as being electrides, so having a free electron that's capable of donating into, for instance, an adsorbed gas phase species, which has some application in trying to reduce diatomic nitrogen in the formation of, for instance, catalytic synthesis of ammonia. And so what this shows is that not only using high-throughput DFT can we generate this huge map of stability that experimentalists can use to find new materials, but we can also parse these DFT-calculated electronic structures to understand what are the chemical mechanisms driving the stability of these materials. So just to summarize this portion of the talk, we use high-throughput DFT and basically double the space of ternary metal nitrides that are predicted to be stable. Collaborators at NREL have confirmed the stability of 7 of these materials that have not yet been reported elsewhere. And we use this newly invented chemical bonding axes to try to understand what is the chemical makeup of these materials that drives their stability or instability. So with that, I'll just summarize my talk. So we've developed these data-driven descriptors of solid-state materials in the space of perovskite stability, including temperature effects in solid-state materials predictions, and then also trying to understand the chemical nature of solid-state materials. And so with that, I'd just like to acknowledge all the many people at University of Colorado, NREL, Fritz Haber Institute in Berlin, and Berkeley Lab, which is my current home institution, but also collaborated with me on the ternary nitrides project, and especially Jack, who was I mentored as an undergrad, who's sitting in the back here. So with that, I'm happy to take any questions. Thank you.